So yes, again, the subject is material, and I'll start with a question. How many materials do you think we have today? So you can just take a guess in your head, don't need to say it out loud. Whoops. If your guess is around 120,000, you guessed right. So that's really an overwhelming amount of choice for product designers and engineers creating new products. So do we need more, or is that enough? And if we need more, what kind of properties should those new materials have? So if we ask a consultant, they might say, you should develop new lightweight material because this is a market sector that's really going to grow. Projection predict 70% increase in the use and demand for lightweight material in the next decade. And this is driven a lot by the need to decarbonize transport solutions. So if we have a lighter car, lighter airplane, they emit less CO2 emission. But even if all the cars are electric cars, we still need lightweight materials because that way they can travel longer distances on a given battery charge. So that the need for lightweight material is not going to disappear. Do we have those materials already? To answer this, we can look at a material property space like this one, where we have strength versus density, and there are different groups of materials are positioned. So you have metal in the far right corner, very strong, but also very heavy. And at the bottom left corner, you have foams, like in your bike helmet, for example. They're very light, but their strength is quite modest. Now, for new material, we would like to be in the top left corner, so incredibly strong and incredibly light. But there's some limits. And this is shown with the dash line here. So to exceed this limit, we would have to discover new bonds between atoms that we have never seen before, and this is fairly unlikely. But you can see that between the limit and the material that we currently have, there's a lot of space for new materials. And this is where we would like to develop new material. That's the target region for development. When I talk about lightweight material, I'm talking about materials with a density below 1,000 kilogram per cubic meter. And to put it simply, this is things that would float on water. Okay? So how can we fill this target region here? Well, one approach is to use metamaterials. Sometimes they're called lattice material, cellular solid. You have different examples here. They are made from a unit cell that we copy in space to create a larger block. And this unit cell can take many different architectures. They are porous, so they're fairly light. The cells can be open or closed, depending on the architecture. And they can be made from any material, metal, polymer, or even ceramics. Now, this used to be quite difficult to make 20 years ago, but now with additive manufacturing, really there's no limit on the architectures that we can create, and even the type of material that we can create them out of. If you wanted a material that's fairly compliant or absorbs a lot of energy, you could use curved surfaces like the TPMS or the Spinodo architecture here. But if you're looking for high stiffness and high strength, straight bars or straight plates are better, so the truss or the plate structure would be ideal. So if you take the truss architecture here and fabricate this out of carbon fiber, you would get strength and density combination that are in the purple bubble there. If you do the same thing but out of aluminum, you would be in the salmon extended bubble there. So we start to fill the target region that I identified earlier with different combination of architecture and material. So is this it? Not necessarily. So when we choose structural material that will carry load, strength is important, but that's not the only important property. Fracture toughness is another material property that characterizes or quantify the resistance of the material to crack propagation. One example of material that has a low fracture toughness would be glass or ceramic. So when they are damaged, they break pretty easily. Metals are very, very tough, and they also have a high strength. So on this material space here, they sit quite on the top right. But here, we don't see density, so we don't see which one is a light material, which one's a heavy material. So if I remove the ones that do not float on the water, now we're left with very few options. We have foams made out of polymer or metal. We have a few plastic, PP, PE are two polymers. And then we have wood. Wood is an excellent structural material. But you can see there's two bubbles for wood, and this is because the properties of wood depend very much on its orientation. So in the best orientation, we have high structural properties, but in the other transverse orientation, then a lot worse. So can we use metamaterial to outperform what we currently have? So my experiments and done by my colleagues as well, we've shown that yes, we can use metamaterial to do a little bit better in terms of high toughness and high strength. So you have here the results of experiments. The red points are titanium metamaterial, and the blue points are aluminum metamaterial. So we can do better than wood, and we also have eliminate some of the disadvantages of wood. So wood is quite sensitive to humidity, but metamaterial less so. So afterwards, in recent years, my group and collaborators, we've used a lot of numerical simulation to identify which architecture offers the highest toughness, highest fracture toughness. You have a qualitative ranking here going from low fracture toughness to high fracture toughness. And what is quite interesting is that the architectures at the top have a remarkably high fracture toughness. It's good to quantify it, but we also managed to identify what is their attribute that makes them so tough. So if we do a structural stability analysis, this is a mathematical equation here, we find that the two architectures at the top have a certain kind of mechanisms that other architectures don't, and this is the attribute that explains their high fracture toughness. Now, I want to say a few words about what we are currently working on now, and I think it's really exciting. So we are not the only one making metamaterial. It turns out that nature has also evolved its own form of a metamaterial. So your bone are porous, so they could be seen as a metamaterial. And wood, if you look at it under the microscope, you also realize that it is a metamaterial. It is porous. It is made of cells. But for us human, when we create a metamaterial, we tend to do something very, very regular. So we have a unit cell and copy it in space. It's extremely periodic. And there's a simple reason for that. It's a little bit easier to make. It's simpler to analyze. But nature does things differently. So you have cells. They're not completely random, but there's some irregularity here. There is some disorder that we don't typically find in man-made metamaterial. And for a while, people thought that this disorder is just a consequence of growth. Okay, nature has to grow those things from scratch. But now we start to have studies showing that this disorder and irregularity is actually an attribute that increases toughness. So now we are working to understand what is the role of disorder on fracture toughness and how can we harness it to make tougher material. So what is the best form of disorder and how should it be distributed so that we maximize toughness? So in summary, if you have to remember only one thing, I would say metamaterial have a huge advantage over conventional material. And that is that we can design them to achieve unique or specific combination of property. And in this talk, I focused a lot on being light, being strong, being tough, which is great for structural application, such as the aerospace industry. But you can also design metamaterial to have other kinds of combinations of property that make them attractive in other application. such as head protection. There's already a type of helmet in North America where they design the metamaterial, they design the protection, and they use different kind of architecture in different locations on the helmet, and they can tailor this solution to different positions. So for different players, they use a different kind of protection. We can also have metamaterial in heat exchangers because their porosity allows fluid to go through and heat to be exchanged. And also in bioengineering, where we can tailor the metamaterial to have a stiffness comparable to that of wood, increasing biocompatibility, and it allows fluid to go through the implants as well. So you may see metamaterial not only in structural application, but in many other applications as well. So finally, I would like to say thank to many people, to all of my group members, past and present, to my colleagues here at Aalto, and my collaborators abroad, and finally to families and friends for supporting the work. So thank you very much.